All right, let's dive in. Today we're talking about a protocol that's basically a master navigator for the internet's traffic. It's called PCEP, and it's one of those unsung heroes working behind the scenes. You've probably never heard of it, but it plays this huge role in making sure our digital world doesn't grind to a halt. So let's figure out how it works. So to really get what PCEP is all about, picture this. Imagine you're in charge of a massive convoy, 1,000 trucks crisscrossing the country. You don't just care about the shortest route, right? No way. You need the smartest route, one that avoids rush hour traffic, is guaranteed to have bridges high enough for your trucks, and doesn't send them down some tiny country lane. This kind of super complex, multi-constraint problem, that's exactly what data networks are dealing with every single second of every day. And that really brings us to the heart of the problem, what I like to call the maze of modern networks. Because, it's not enough anymore to just get a packet of data from point A to point B. It has to get there efficiently, reliably, and without messing up the experience for everyone else. Now, there's a technical name for this whole process: traffic engineering. The RFC we're looking at defines it as managing traffic to get the absolute most out of your network. Think about it. It's what makes sure your really important video call doesn't get choppy just because someone else on the network started a massive file download. At the end of the day, it's all about optimization and performance. But here's the catch, and this slide nails it. An individual router, on its own, is like one of those truck drivers with just a local map. It can see the next few streets, the next couple of turns, but it has absolutely no clue that there's a huge traffic jam 100 miles up the highway. This lack of a big picture view makes it pretty much impossible for any one device to figure out the truly best path from start to finish. So, if the individual drivers can't solve this puzzle on their own, what's the solution? Well, you need a central dispatch, right? You need a master navigator that has that bird's eye view of the entire system. And this is where we meet the two main characters in our story. On one side, you have the Path Computation Client, or PCC. That's our router, our truck driver. It's the client that needs directions. On the other side, we have the Path Computation Element, or PCE. This is our master navigator. It's a powerful central server with the complete map, all the live traffic reports, and the brain power to calculate the perfect route. The PCC asks the questions, and the PCE finds the answers. So let's be super clear about what a PCE is. The RFC defines it as an entity, which could be a special application or a dedicated server, that's whole job is to compute network paths. It takes in the entire network map, this huge graph, along with a list of all the rules and constraints, and it just crunches the numbers to find the best possible way through. It's literally the brains of the operation. Okay, so we have our client that needs a path, and we have our master navigator that can figure it out. But for this whole system to work, they've got to be able to talk to each other. They need to speak the same language. And that language, you guessed it, is PCP. This is the very core of RFC 5440. It is the specific set of rules, the grammar, the vocabulary, that lets a PCC send a request over to a PCE, and for that PCE to send a coherent answer back. It's so flexible, it even lets two PCEs talk to each other to solve even bigger, more complicated problems. And here's a neat little technical detail for you, straight from the source. This whole conversation happens over TCP, which is a reliable protocol, and it uses the officially registered port number 4189. Using TCP is super important because it makes sure that none of these crucial messages get lost or mixed up along the way. All right, we've met the players, and we know the language they speak. So now, let's actually walk through what a conversation using PCEP looks like. Before any real work can get done, the PCC and PCE have to get properly introduced. It's a pretty simple three-step handshake. First, they just open up a normal TCP connection. Second, they swap these open messages to agree on the rules of the conversation. And finally, they start sending keep alive messages back and forth just to make sure the line is open and they're both still listening. So, once that connection is solid, we get to the main event. How does our client, the PCC, actually tell the master navigator what kind of path it needs? It uses a special message called a Path Computation Request, or a PCREQ. And you can think of this message as a super detailed shopping list. The PCC packs it with everything it needs. First, the basics, the endpoints, where to start and where to end. Then, a crucial one, bandwidth, how much capacity it needs. It can also specify a metric telling the PCE to find the absolute shortest path, or maybe the cheapest one. And it can even get fancy and ask for special attributes like making sure the path has a built-in backup route. So the PCE gets this shopping list, goes off and does its number crunching, and then it sends back a reply. And really, its answer, which is called a PCRP message, can only go one of two ways. In the best-case scenario, it's a positive reply. It says, yep, I found a path for you, and it includes something called an explicit route object, which is basically the turn-by-turn directions. But if it can't find a path that ticks all the boxes, it sends a negative reply with a no-path object, which very helpfully explains why it failed. So what are some of those reasons it might fail? Well, the RFC outlines a bunch. The most common one is just that there's no path in the whole network that meets every single constraint. Like maybe the bandwidth request was just way too high. Or maybe the destination doesn't exist. Or it could even be that the PC itself is just too busy at that exact moment. The protocol has a way to communicate all of this back, so the client isn't left guessing. Okay, I know this has been a bit technical, but understanding how it works is so important to see just how big of an impact PCEP has. So let's zoom out and talk about why this protocol really truly matters. This is the payoff. This is what PCEP enables. We're talking about networks that are just fundamentally smarter. It helps internet providers get the most bang for their buck out of all their expensive equipment. It helps prevent those annoying network slowdowns by finding clever ways around congestion. And it enables really cool high-end services, like finding two totally separate paths for a bank's critical data to make sure it's ultra-reliable. It is the absolute key to having centralized, intelligent control over traffic. And what's just brilliant about PSCP, and this quote comes straight from the source, is that it was designed with the future in mind. The people who created it knew that network needs would change over time, so they built it to be flexible, to be extensible. That means as new tech comes along, PSCP can just evolve with it. You just add new message types, new items to that shopping list. And that really leaves us with this one big final thought. We've seen how PCP helps find answers for the networks we have today. But as we start moving into a world that's going to be dominated by AI, the Internet of Things, and things like 6G, the complexity is just going to explode. So the real question is, what new, even harder questions are we going to need our master navigators to answer in that future? And will PCP be ready for the challenge?